Yeah, first I'd like to start by thanking the organizers for this very nice school. So today my talk's going to be a little bit different. First, I don't have the nice polished slides from the previous talks, but you're going to have to deal with my handwriting. And also I'm going to talk not so much about topological band structures or superconductivity, but instead about anions and intrinsic topological order. So my goal over the two lectures is to introduce you to the basics of anions and how to describe them in terms of topological quantum field theory. And I'm going to focus on non-abelian anions because these are the more general case. And in particular, I'm going to talk about Fibonacci anions. So all of these should just be words at the moment, but hopefully by the end, all those words make sense. So a plan for the two lectures is as follows. I'm going to start with a bit of background and motivation for this, which has been made easier for me by this morning's talks, which gave a nice overview of topological phases. But I'll talk about how these intrinsic topological phases fit in. And then I'm going to revisit bosons and fermions, which we're all happy with, and then talk about how this is not the only option in condensed matter physics, but we can end up with these anionic excitations as well. And then in this first lecture, I want to kind of state things. I want to give you observations about anions, how they behave, and then in the second lecture, we're going to develop a theory, a model for these anions. And this is this TQFT, and this involves the anions themselves, ideas of fusion, some F moves, R moves, all of this stuff we'll get to, and kind of the exciting stuff that comes out of this is the ideas of braiding and topological invariance that we can compute using these models. Okay, so very simply put, anions are particles that are neither bosons or fermions. They have different statistics that is not captured by these two particles. But they don't exist in nature as free particles, but instead as collective excitations in topologically ordered 2D systems. So let's start with this idea, like what is topological order? And now this is let's start from the opposite side. Like what is topological order not? Like what came before that? And this is kind of the traditional view of phases and phase transitions in terms of symmetries and local order parameters. Okay, so many phases can be understood in terms of the symmetries of the system and the transition between them in terms of symmetry breaking. And characterizing which phase you're in can be done by looking at the system locally, looking at local order parameters. Topological phases, on the other hand, cannot be distinguished in this way. We do not have these local order parameters, and we need not have symmetries to define the phase or have symmetry breaking between different phases. Now, this is quite general. There are different types of topological phases, things that go beyond this simple picture. And this list is not exhaustive, but they're kind of the broad strokes of the cases that we can have. So we've heard a bit this morning about free fermion or topological band structure systems. Also a bit this morning about symmetry-protected topological phases. So, for example, in one dimensions, everything is trivial, except when we have some symmetries, we can again get topologically distinct phases. Then what I want to talk about is systems that have intrinsic topological order, which are described by these TQFTs. And we can also go further. Like once we have this topological order, we can add symmetries and impose symmetries, and again, the story gets richer. Okay. And yeah, I just mentioned that some of these things were talked about this morning, much better than I would. So I'm just going to skip to the bits that I'm going to talk about. So why do we care about this? This is always a question that I try to ask, like why do we care about these systems? Like topological systems in general, we heard a lot this morning about advances, particularly on the topological band structure side, and why these are useful. But more specific to the topological order, there's this concept of topological protection, that we can have quantities that are protected against local perturbations. These are non-local objects that are not sensitive to imperfections in our system. We also have this deep connection in these systems between ground states or degenerate states of our system and the types of excitations that can appear in this system. Okay, so this is not at all obvious, but there is this deep connection between these two things. The third one I mentioned is probably the one that gets mentioned the most. Is it's going to revolutionize our quantum technologies. They perhaps provide a way of doing quantum computation, but more concretely, there seem to be applications in quantum memories or, for instance, quantum error correction. That essentially use these anyons. And also, there's deeper questions that we can maybe talk about in this context. And one concrete example is something that we proved recently, that if you have certain intrinsically topological systems, then this topology is related to what's called an intrinsic sign problem. Basically, this topology actually poses an obstacle, a fundamental obstacle, to classically simulating that system. Okay? So then there's, again, some more fundamental questions that come up about computational complexity. Okay. And as a final part of this background, before I start talking about these anyons, where do we see these anyons? What kind of experiments or systems do we find them? I think most famous example is in fractional quantum Hall systems. So these are believed to be described by topological phases and host anyons, which can be abelian or non-abelian. And again, I'll tell you what that means a bit later on. But very recently, a couple of years ago, there was an experiment in fractional quantum Hall systems, which they coined as an anion collider, where they were able to essentially see signatures of these fractionalized excitations. And the simple picture is that they have fractional quantum Hall systems with these edge modes that they bring very close together. And when they're close together, these anyons can actually interact with each other. So much like, this picture now looks a lot like the particle collision experiments. We have these modes which come together, they interact, and they fly out, and then by measuring them, we can see signatures of the anionic excitations. And this showed that the excitations are indeed fractionalized. They're not just the electrons, but these also turn out to be of the abelian type of anyons. In a slightly different system, so we have some magnetic systems, such as this alpha ruthenium chloride. These are believed to be described by, they're believed to be proximate to spin liquid states, the ground states of these systems. In particular, it's believed to be described or approximately described by the Kitaev honeycomb model, which has mobile Majorana fermion degrees of freedom. And this has been kind of seen again indirectly by, I think this is thermal Hall measurements. If we had itinerant fermions, we would get this value of 1. But the temperatures that they looked at, they found this fractional value of 0.5, indicating that they do indeed have these Majorana degrees of freedom and not just these fermions. And the final example I give is of realizations of Kitaev's toric code. The toric code is a very important example because it's pretty much the simplest topologically ordered system that you can write down. It's also important because it is one of the leading proposals for error correction in quantum computing to use the toric code. And this was recently realized experimentally by Pedram's group at Google. Also, I was lucky enough to be part of that collaboration where we realized the toric code on this system here. So you'll recognize this kind of picture from Pedram's talk where these crosses are the qubits. So we realized the toric code ground state and played around with these anionic excitations of the toric code. And in parallel, Misha Lukin's group realized the toric code Hamiltonian in trapped Rydberg atoms. Again, this is a slightly different flavor, but there they have a Kagame lattice of Rydberg atoms, and they find that they have this kind of dimer spin liquid, which is essentially the same thing as the Kitaev's toric code. Okay. So now that's a bit of background. So let's start properly with describing anyons. So again, before describing anyons, let's go back and talk about fermions and bosons. So we all know that all particles in nature that we see are either bosons or fermions. And the difference between these two types of particles can be neatly summarized by kind of a thought experiment where you swap two identical particles. Now, if we have two indistinguishable bosons and swap them, then we end up with exactly the same state, with a positive phase. However, if we do the same thing with fermions, we end up with the same state, but with a minus sign out front. Okay, now this very small difference, this minus sign, is extremely important. And this leads to a huge range of ramifications, such as the Pauli exclusion for fermions, which is, we wouldn't really have chemistry without this Pauli exclusion principle. We have this deep connection between fermion boson statistics and integer and half-integer spins in the spin statistics theorem. We also have like Bose-Einstein condensation for bosons, and as we heard about this morning, superconductivity for fermions. So the difference in this minus sign really does lead to a huge difference in the physics that we can see. But then you might ask, why is it only two? Why is it only bosons and fermions? Is there anything else that we can get? And so again, let's go back to an argument that you've probably seen for why these are the only two options. So let's consider these two indistinguishable particles again, but now let's give them a label that allows us to keep track of them for this thought experiment. Okay, so I have particle A and I have particle B, but they're indistinguishable. Now, if I swap them once, then I get back to the same state, but let's allow a general phase to come up, this e to the I phi. Now, if I swap them again, I really do end up back at the same state, and even my fictitious labels are back in the same place. Okay? But now, it's the same swapping, so I'm going to pick up an extra phase of e to the I phi. Now, what we can do is change our perspective. Let's go to the center of mass of particle A, and then what we've done is we've just taken B in a full circle now around A. So if we swap twice, it's the same as just taking B all the way around A. Now, if we live in 3D, which we do, the path that we've taken is not important. I can smoothly deform this path, and importantly, I can take this out of the plane. I can take this path that B's taken out of the plane, and then I can deform past A right to a point. So this process of dragging B around A is really the same as just dragging B in a little circle that doesn't encircle A. And so I can close this loop all the way up, and so I deduce that this phase e to the 2I theta must equals 1, which leads to the fact that there are only two options for this exchange of fermions and bosons. Okay? So the important part here in this argument is that we're in 3D. Okay? This idea that the path that we take doesn't matter, and going around the particle, it's not really an actual obstruction. I can equally just do this loop away from particle A. However, if we lived in 2D, then this option is no longer available, and this particle A that's sitting there really is an obstruction. I can't just close this loop anymore and have it be the same process. Okay? So very simply put, it's more complicated than this. If we lived in a 2D world, then particles would be allowed instead to have a general phase e to the I phi. This would still be a possibility. And the allowed particles would be what we're calling anyons. Now, all of this is simplified, and it turns out anyons is also a bit of a misnomer. Not any phase actually turns to be allowed. Like, these have to be rational phases, and then also, not all rational phases are allowed. But the main point is that if we're in 2D, then more possibilities are available. Now, the minus sign for fermions had huge ramifications. Now we've got a more general phase. It turns out to be, an even richer story. Even with just this phase, we end up with a much more complicated structure for these anyons, and that's what I'm going to talk about here with this description of topological quantum field theory. Right. So please do stop me at any point if you have any questions, but let's now just go into some observations about anyons. So here I'm really just telling you how anyons behave and some of their weird properties, and then in the second lecture we'll build up the mathematical description of them. Okay. Okay, so I gave a very loose argument just then that if we have anyons, then exchanging two indistinguishable anyons, I can pick up now a general phase, which I have written here as theta A. Okay, so this I can call the topological spin. Sometimes it's called the topological twist. These names seem to crop up in slightly different places, but let's call this the topological spin. Now, as well as the exchange that can be different to fermions and bosons, there's actually another type of statistics that doesn't really make sense in 3D for fermions and bosons, and this is the mutual statistics. So now if I have two anyons that are distinguishable, I can drag B around A, and this is not just going to give me back the original configuration, but I can also pick up a phase in this case. Okay, so again, like if I were in 3D, then the argument that I can just close this to a loop would say that this should always be trivial. In 2D, I really am always enclosing this particle. This particle is an obstruction to closing this loop. And so again, I can pick up a phase in this case. Yeah.
So indistinguishability is not crucial for exchange statistics?
So indistinguishability is important for the exchange. Okay, so if this was red and I swap them, then I would now have blue-red rather than red-blue. Okay, I can tell those two apart. I can measure the left particle's red, the right particle's blue. And if I swap them, this is really a different state. your particles are in different places.
Sorry, I think what I mean is mutual is just trivial for fermions and bosons.
Yes, so the mutual, yes, if we're in 3D, then this is, this doesn't, it doesn't really make sense. This is always going to be trivial. But now we're in 2D, this can also be a non-trivial process that you drag something around. You end up back in the same configuration, but the process of doing something and going around this particle A can lead to a non-trivial phase. Okay. Right, so then we have these extra phases, which I'm going to call the S matrix. So this phase now depends both on particle A and particle B. Right. So, you know, if you see these things, then these topological spins are often summarized in a slightly different way. They're often written in something called the T matrix. Now, the T matrix is just the diagonal matrix, where on the diagonal you've put these topological spins. Okay? But the point being that the statistics of anyons now is described by this T matrix and the S matrix. Okay? And these are much more general things than just the -1 that could crop up for fermions. Okay. So let's give you an example. Let's be concrete. Let's turn to the toric code. So I expect that you've all seen the toric code. I would ask who's not seen it, but I don't think anyone will put their hands up anyway. But, so the toric code, I expect you to have seen, and if you've not, you should probably look it up. It has 4 types of anyons in this model. We have the vacuum, so something that we'll come to see. In our anyons, we always list no anyons as an option. Okay, so this is what I mean by vacuum. It's the absence of anyons. We also have an electric excitation, a magnetic excitation, and then a composite excitation, which sometimes written as phi, sometimes epsilon. So these are the excitations of the toric code. Now, the T and S matrix for the toric code are as follows. We have 1, 1, 1, and -1 for the topological spins. And importantly, what this means is that the electric and magnetic excitations are bosonic. Okay, so we have this +1 sign. And the composite excitation is a fermion. Okay? So already we should see something a little bit funny here. We've combined a boson with another boson, and we've ended up with a fermion. Okay? So something's already a bit fishy here. So now we also have the S matrix. This is the mutual exchange of these anyons. Right, so for example, this value here of -1, this basically says if I take an E excitation and I take a magnetic excitation around it, then I'm going to pick up a factor of -1. Okay? So is it clear to everyone what each element of these matrices means? Okay? And it's really this exchange this mutual statistics, this -1, which explains how we're able to get that this epsilon is a mutual fermion.
Like only the different types of excitations are distinguishable, but not 2 excitations of the same type, right?
Sorry, can you repeat that?
You said for this mutual exchange, they are particles or the excitations are distinguishable. They are only distinguishable in the sense like you can distinguish between like E and M, but not 2M. Right?
Okay, so I mean, in general, mutual holds even if they're distinguishable. We also have mutual statistics for distinguishable particles. In this simple case of the toric code, this is really just exchanged twice. Okay, so just this diagonal in this matrix. For abelian models, this is not generally true for non-abelian, but this is literally just theta A squared on the diagonal. Is that?
If I would just
Yes, but talking about thermodynamics of them is, what do you mean by that?
Or like if I exchange two of your blue dots,
Yeah.
like what kind of statistics are they distinguishable or not?
They're indistinguishable, right? So if you have two M particles, they're just two M particles. Like if you swap them, there's no extra label to tell you which way round they are. They're indistinguishable. Yeah. Yeah. Okay. So now let's turn to the example that I promised of non-abelian anions, and this is the Fibonacci model. So this is the simplest non-abelian model, but it turns out it has nearly all of the features of like a most general non-abelian model. In particular, it turns out that these Fibonacci anions, if you do topological quantum computation with them, which again I'll come to, these are universal. So you can really, by dragging around these Fibonacci anions, you can really do any computation you want. And I'll come to how that works. Okay, so now let's look at the statistics for these particles. So we have, again, the vacuum, which I write as 1, so no anions. And we have this one Fibonacci anion, which I denote with a tau. And people have flagged this up before. I write taus a bit funny. You might normally write them something like that. Okay, so now the tau anion has a phase which is not plus or minus 1. It's this rational phase e to the 4 pi I over 5. And then we also have the S matrix, which is as follows. We have now the golden ratio showing up here. So we have this phi is the golden ratio. And I'll delve in a bit deeper why this golden ratio comes up. But with the name Fibonacci, maybe it's not so surprising that this crops up. Okay. Yeah, it turns out that this thing here, this phi, this is something called the quantum dimension, and it's related to how fast the Hilbert space grows if we add more and more copies, more and more tau excitations to the system. Okay. Yep.
Just quickly, with this, because the T matrix also includes both the topological spin and the part that comes from S. Yeah. So if I would just like to extract that theta, the topological spin that you wrote before, I would have to.
So this is just here. So this is just theta tau. Okay, so T is just the diagonal matrix where you've put in the diagonals, the topological spin of the anions. That I write it as a matrix is maybe a bit confusing, but this is standard, and it comes from maybe a deeper representation of these TQFTs. Yeah.
What is the meaning of taking no particle around?
It's just taking no particle around it. It's doing nothing, and that's why. So yes, so that's a good point. So let's go back, because I did cheat you slightly here. Here I talk about dragging a particle around another, and you're saying, well, what does it mean if I drag the identity nothing around A, and I somehow get something that's not 1, right? So if I went too far. I've now got something that's not 1. Turns out that this guy that I wrote here is not actually S. It's something called the monodromy matrix, MAB, and this is proportional with some factors of these quantum dimensions. There's some relation. It's related to SAB. I don't want to go much further. I don't want to go into details of the relationship between these two, but like actually dragging a particle around in an experiment, you will get the monodromy matrix. But the underlying topological invariant that we care about is this S matrix. So this might become clearer when we get into the second lecture. Okay. Right. So Yeah, so we talked about like what if we lived in a 2D world, like we could get these anions, but that's cool. But why do we care? Like this is some we're playing a game now that, let's say, we live in 2D. Well, it turns out that this is not just theorists playing a game. It turns out that we can realize effective 2D systems in the experiment. And a famous example of this are the graphene experiments, where this really is an atom-thick experiment, and also in the 2D electron gases in quantum Hall systems. And the fractional quantum Hall systems are believed to be exactly these topologically ordered phase that host these exotic anion excitations. Yeah, and then, I guess I've already kind of said this, that we care because these anions, it's not just about these particles, they're really another way of talking about intrinsic topological order of quantum states. And we'll come to this idea that non-abelian anions could actually be useful for doing braiding or computations. Okay. Any more questions at that point? Yeah.
How do you have to have anions? If you have a 3D system that's only periodic considerations, does that work somehow?
Yeah, that's a good question. I don't know. Yeah, that's a good point. So I don't know the answer to that. There will be some, sense that it's 2D. Like it's never truly 2D, right? We do live in 3D, but you can realize these effective 2D systems. I mean, it's probably going to be very specific to the setup, but I think you can believe that like these quantum Hall systems are realizing these 2D electron gases, and that they do exist, and we can really think of them as 2D systems.
Maybe I missed it before, but a lot of the properties that you mentioned, they will also speak, for example, the Majorana edge modes at the edges of one-dimensional wires, for example, will also be anions. But you said they're not photons or fermions anions. So how you would view these Majoranas?
So you can have Majorana anions, but the Majorana edge modes that you're talking about would not generally be described in this way, right? So these generally are like zero modes of a system and live at boundaries. So strictly speaking, they're not the anions I'm talking about, but it turns out that you can take these edge modes and braid them like in these T-junctions, and you really can extract the same kind of stuff that I'm talking about here. Yeah. But here I'm really talking about, I have a 2D topological system, and I have point-light particles living in this 2D system. Yeah. Okay. Great. So, yeah. So again, I'm just telling you things today, and we're going to go deeper. But one thing that kind of shows up when we relax this statistics of the anions is another concept of fusion of anions. Okay, so these may not seem related, the fusion of anions and the statistics, but it turns out that they are related. But let me tell you about what fusion is and how to think about it. So there's two ways to think about the fusion of anions. The first is that we just take two anions and we put them together, and they make a new particle. Okay, so we take A and B, we put them together, and we now have a new particle C. That's one way to think of it. Another way is that we have particle A and B in some region, and we kind of zoom out, and we think of that whole region containing them as its own entity, which has its own behavior and actually behaves like an anion, collective anion C. Okay? So to be more concrete, let me give you two examples that you will have seen in different contexts. So an example of the first case is just particle-antiparticle annihilation. If I take a particle and its antiparticle, I bring them together, they will annihilate, and I will be left with no particle. So I've started with an anion, an anti-anion, brought them together, and I'm left with the vacuum anion. I'm left with nothing. Okay? An example of the second case is that if you have two fermions together, they can behave collectively like a boson. Okay, so if I have a hydrogen atom, I can think of the hydrogen atom as a point-length particle, but we know that inside it actually has a proton and an electron, which are both fermions. Okay, but the hydrogen atom collectively behaves like a boson. Okay? So these are two ways of thinking about if we put multiple anions together, they behave like another anion. And mathematically, we're going to write this as a fusion rule. I just flash it here. We'll come back to what this means. But what I've written here is that A and B can fuse to anion of type C. Okay, so I'm using here general labels. A and B are just two types of anions. Fuse them together, and I get anion C. However, that's not the whole story. It gets more interesting with non-abelian anions. Okay, so what is possible is to have multiple fusion channels. So if I take this equation here, I can generalize it and write that A and B fuse together, and I can get anion C, or I can get anion D. There are two possibilities. And actually, this is the definition of non-abelian. If there are multiple possibilities for the fusion, this is a non-abelian model. If there's a single possibility for the fusion, this is abelian. Okay, but what on earth does this mean? I brought them together, and I've got two possibilities for the fusion. So again, this sounds weird, but is something that you've probably seen before. A good analogy of this is the combination of spins. If I have two spin half degrees of freedom, and I think of them collectively, I bring them together, then I can actually split this into two parts. There's the singlet part, and then there's the triplet part. Okay, so the singlet really acts like a spin 0, and the triplet acts like a spin 1 degree of freedom. Okay, so the combination of two spin halves, I'm saying, is a 0 plus 1. Yes, and so really the definition of non-abelian is that we have multiple fusion channels. And the Fibonacci model is an example of this. So if I take two tau anions and fuse them, then they can either behave like the vacuum, like a boson, or they can behave like another tau anion. Yep?
There's no notion of symmetry here, though. It's just an analogy of stuff. Or you don't need a...
Yeah, it's just an analogy. It seems to go pretty far, this analogy, but it's just an analogy. Really, the way we should think about this is like in the possible states. So really, this fusion rule, it tells you what states are possible. If I have two, A and B in a region, then there are different possibilities for the states that they can exist in. One where collectively they behave like C, another where they collectively behave like D. Okay, and that's kind of the point of this box. Like, what does it mean, C or D? This fusion rule gives you the possibility of the states. Now, the actual state of your system will be some superposition of these possibilities. Okay, so your A and B can be in C, it can be in D, or it could be in superposition of these. Okay, and so this idea of fusion seems to have come out of nowhere, right? I'm just telling you that fusion, is a property that these anions have, but it turns out that the fusion rules can be deduced from the S matrix. So if you know the mutual statistics, you can actually go back and find out what are the fusion rules for these anions. Okay? I'm not going to explain this here, but this turns out to be true. And again, it's an example that just adding a phase or just going a bit more general, you end up releasing a whole richer structure for these particles. Okay, so let's get on to kind of the exciting part, which is braiding. So far, we've only looked at the properties of a pair of anions. Okay, so if I exchange a pair of anions, or if I have this mutual statistics, or I fuse a pair of anions. Now let's go to the next case, which is let's have 3 anions. And now things get a bit more complicated, and we start to see the more general structure. Okay, so yeah, with more than 2 anions, we can introduce the idea of braiding, which is essentially the idea of rearranging our multiple anions. Say we have 3, we want to swap pairs of them and rearrange this array of anions. And just as a note, like the exchange and mutual statistics are special cases of this, but when we go to more particles, there are more possibilities. Okay, so the Fibonacci anions have the following fusion rule, which is 2 taus confused to the identity or to tau. And what this means is that if we have 3 anions, there are 3 possible states. And this is what I draw here. So I have 3 tau anions, and the blue ring is the collective behavior of the first 2, and the green ring is the collective behavior of all 3 of them. Okay? So the first 2 could fuse to the identity, and then the 3 of them could fuse to tau. The first 2 could fuse to tau, and all of them fuse to tau. Or the final option is that the first 2 fuse to tau, and then collectively they all behave like a boson. So these are the 3 options that you have when you have 3 anions.
Can't they all, first 2 not fuse to 1, and then all of them also to 1?
Because if the first 2 fuse to 1, then you have the fusion of 1 with tau. So you have the fusion of nothing with tau. So this is going to be tau. If you have nothing fusing with tau, there's no way that collectively this behaves like nothing. Okay? So this is going to show up, but we always have the rule that the identity fused with any anion is the anion itself. Okay? Yeah, so that would be an option that's not allowed here. Okay, and in connection with topological quantum computation, these are given particular names, 0, 1, and n. And the reason for this is that this 0 and 1 turn out to be the 2 levels of a qubit. Just as Pedram was calling them 0, 1, and 2, we have the same kind of notation here for these states 0, 1. And n here just means it's non-computational. Okay. Right, so now these are the possible states. Let's consider braiding these anions. So we have these 3 anions here. And the first thing I'm going to do is consider braid A, which is just swapping anion 1 and 2, the first 2. The other option I can think of is braid B, where I swap the last pair. Okay? So these are the 2 different swappings that I can do for these 3 anions. And now let's think about what happens in this description. You know, if I'm grouping these as so, like I group the first 2 and I group all 3, then this braid is actually just happening for braid A. This swapping is just happening within this first loop. Okay? So what this tells you straight away is it's not going to change the state. All it's going to do is introduce a phase. Okay? So, you know, this label of this loop is not going to change because this swapping is happening inside. However, for process B, if I've dragged the second one and swapped it with the third one, then, you know, I know that it's now these 2 that had the fusion channel I started with, right? So if I take this picture and I swap the last 2, then I know this grouping. Okay? But this is not one of my initial states. Okay? It turns out that this is going to be a superposition of these guys. Or said another way, this process is not going to give me a phase, it's actually going to give me a matrix that rotates within this space of states. All right. So let's introduce a matrix vector notation. Let's just write these three basis states as follows. Then braid A can be written as the following matrix. So each state will stay the same, but it will pick up a phase. And this phase will depend on which state we're in. Okay? So now it doesn't just depend. I've swapped two tau anions, and it doesn't just depend on the fact that it's two tau anions. It actually depends on the other tau anion that's in the system. Okay, so this is already something a bit richer than just swapping two fermions. The exchange statistics now depends on the fact that we have other anions in the system. Then braid B can be written as this matrix. So this braid B, it doesn't keep us in the same state. It's generally a matrix, and it can be written as follows. Now, it turns out that this matrix is block diagonal, and this is why we call this final state non-computational. We can actually separate out the 0 and 1 and this non-computational state. Those two sectors never get mixed up. Okay. Right, so let us focus on that 0, 1 subspace, because we can forget about this non-computational state. If we don't start in it, we'll never see it. So let's just focus on those 0 and 1, and we get these smaller matrices. Now, it turns out that by taking just these two matrices, sigma 1 and sigma 2, and taking lots of products of them and their inverse, I can get to any 2 by 2 unitary matrix I want to arbitrary precision. Okay, so you give me a 2 by 2 unitary matrix that you like. I could find a way of taking a product of just these two very, very many times to get as close as I want to that matrix. And what this means is that the Fibonacci anions are actually universal. So I can approximate any unitary I want just by braiding these Fibonacci anions. Now, it turns out if I go to more Fibonacci anions, so more than just 3, then I can actually approximate an arbitrary size unitary to arbitrary precision. Okay, and this is really the goal of quantum computation. We want to simulate a unitary on many qubits, and by doing this braiding, I can do this to arbitrary precision. So this is really the idea behind topological quantum computation. Yeah.
So for the anion situation, you can reach any point of the loss here?
Yes. Yeah. Yeah, it doesn't seem obvious that you can do that, but it's true.
Is it very efficient? Like, do you only need very few products? Or is it
No. So that is one of the problems. It may turn out to just be like a engineering problem, but one of the problems with topological quantum computation is that you need very many products to approximate the gates that we want. Or maybe maybe a better way of saying this is we typically, as theorists, think in a certain gate set. Like we might use the Pauli matrices or something like that. Now, to get to those from these matrices is very complicated, right? To go back to the gates that we like takes a long string, and then we could do computations with that. But that's maybe not the way to work. Like we could instead work directly with these and know that we can do any computation. It's just a question of how to write our algorithm in terms of those, rather than the gates that we're more comfortable with. Yeah.
Why is there no braid C where you exchange the first and last of the 3?
First and last, so that is a composition of these two. Okay, by doing A and B, you can do it so that you've swapped the first and the last. Okay. Right, so that's pretty much everything I have to say. So, like I said, I've kind of told you things. I've spat these matrices at you, but what we will do in the second lecture is we will actually build up the model. We'll start with the anions, we'll add ingredients such as fusion and braiding, and we will actually compute these matrices. So we'll put in the tau anion theory, and we'll show that we can get out these matrices for the braiding. So that's kind of the goal for the second lecture. Thank you.
Questions? More questions?
As you increase the number of anions, computationally space also grows, or is this one dimensional?
Yes, so the way that you would do this, rather than just adding, like going to 4 anions or going to 5 anions, what you would typically do is take these 3 as your unit for a qubit, and then you would take another 3 as your second qubit. So now you can see how the non-computational space grows. You have, a non-computational space for each of these, and etc. Does that make sense?
Yeah.
Yeah.
It's a really lame question, but in real life you can have decoherent size flows, so can you reasonably reach every point in the bloodstream? Like if you have to do 10 million of these operations, that takes some time, right?
Yes, it takes some time, but that's kind of the point of topological quantum computation, is that it is protected against like local perturbations, which outside noise typically is of this form. So if you make your system large enough, if everything's separated far enough, then you can essentially beat this noise. Everything will take longer, but you will be able to do this more accurately, be less susceptible to this noise.
But do you have like an upper limit of the amount of these matrix because you have to do to reach every point? Like what's the most you have to do?
To get to a particular point, like, you'll never get to that point. Like, it'll always be to that point with a given accuracy. Okay, so yeah, that's the way that you have to think. Yeah, but there's theorems that you can do this in a certain gate depth for a particular accuracy, kind of thing.
So, it seems like this braiding relies on this matrix structure of the anions, right? I guess you have this golden ratio in there that you can actually reach by taking products all points on the block sphere. So could you have usually if you find any anion, can you do the same thing, or are there also boring anions where you can't?
That's a very good question. So another example of important anions is the Ising anion theory, where you have the identity, you have Majorana fermion, and you have a fermion. Okay, and in this case, rather than having this golden ratio coming up, which you've maybe realized is an important point, you end up having a square root of 2 coming up for this Majorana fermion instead. And it turns out in this case, it is not universal. Okay, so you again have this matrix structure, but by taking products, you can't get anywhere. Okay, so it's still more general than fermions, but it's not universal.
The root of some irrational number or something to
Well, I mean, this is still an irrational number, right?
Well, yeah, but squaring it, not.
Yeah. Yeah, I mean, I can't give you a general rule, but it turns out this case is not universal. Fibonacci turns out that it is universal. And yeah, that Fibonacci, the golden ratio, of course, is part of why that's true. Yeah. So if you have a phase that's not 1, you will also have Pauli exclusion principle.
So for everything that is no boson, there is a Pauli exclusion.
You have a Pauli exclusion principle, yeah, and it's for the same reason that you have it for fermions, right? You pick up a non-trivial phase from exchanging them. So if they really sit on top of each other, you have an ambiguity in the phase. Okay, so yeah, all anions except for the bosons also have Pauli exclusion. Thank you.